Okay, so our next speaker is Andreani Petrou from Okinawa Institute of Science and Technology. And she will tell us about knots, links, and Harer-Zagier factorisability. So whenever you're ready.
Thank you so much for the introduction and for the opportunity to speak here. So yes, I will be talking to you about my research with my PhD advisor, Shinobu Higami, which is available on arXiv. And indeed, it's about knots and links and a property of them that's called Harer-Zagier factorisability. But before getting there, let me mention that humans have been interested in the ability, have appreciated knots for their ability to encode information since very ancient times. And here you can see examples of various civilizations that have used such devices, which consist of string or rice straw and knots tied into it as an alternative of a writing system. So they could write using knots. And from the mathematical viewpoint, of course, we're interested in topological information that is encoded in knots. And this is extracted using polynomial invariants, such as the HOMFLY polynomial, which we denote by h, and it's a two-variable polynomial that can be defined by this skein relation and the normalization condition that for the n not is equal to 1. So to demystify how this works, let's consider the example of the trefoil knot, which is a torus knot with 2 strands and 3 leaves. So by choosing an orientation, focusing on one particular crossing, we see that we are on this configuration here. So we throw everything else on the other side, and this tells us that we get a factor a squared when we switch from over to under. This is what I'm doing here, if you can see, and this is what this tells me to do. And then on the other side, we get factor z times a when we connect these two strands and these two strands together. So this gives us this link, and we can keep doing this until we get to unknots with value 1, and summing everything up gives us this HOMFLY polynomial for the trefoil knot. And another polynomial that is interesting, it's called the Kaufman polynomial. It's also two-variable polynomial and has a similar definition in terms of skein relation. And I don't go into the details of computing it, but for the trefoil knot, I give you the answer so that you can observe that is in general more complicated than HOMFLY and involves both odd and even powers of a and z, in contrast to HOMFLY, which for knots only contains even powers. And these polynomials have a nice, are unified in the framework of Chern-Simons theory according to Witten, which basically tells us that they can be obtained by averages of Wilson loops corresponding to some particular gauge group. So the HOMFLY polynomial corresponds to the choice of SUN. And in fact, this average will give us a quantity that we call the unnormalized version because it involves some overall multiplication. And this theory also prescribes a change of variables. So in terms of Q, which is a parameter depending on Chern-Simons theory. And now, yeah, we replace A with Q to the power n being the rank of the gauge group, and Z is equal to Q minus 2 inverse. And similarly, the Kaufman polynomial corresponds to the SON plus 1 invariant with now this normalization factor. So the Harer-Zagier transform, basically it's a tool that originates from random matrix theory, and it was used to compute Euler characteristics of the moduli space of Riemann surfaces. And it has been recently proposed by a group of theoretical physicists that it could be applied to knot invariants that are polynomial in Q to the power n. And in this context, it just takes the form of an infinite sum over n and replaces the variable n into a new variable lambda. And the way to compute it is basically using geometric series after if the series is convergent, of course. So this would tell us that every monomial in Qn to some integer power under this summation will be mapped to this rational factor 1 divided by 1 minus lambda q to that integer power. So the effect of this transform is that it eats a polynomial and spits out a rational function in lambda. So let's see how it works for our favorite example. So we had this HOMFLY polynomial that we computed earlier, and then we changed the variables, but leave a as it is for now, also multiply by the overall factor. And now we have this result. And basically, evaluation of the Harer-Zagier transform is replacing all a, which, if you recall, was q to the power n, by this factor. And this is what we're doing here. Basically, a now becomes this 1 minus q lambda, and a cubed corresponds to this factor, a fifth to this one. And in the process of taking a common denominator, we get a very simplified expression on the numerator. And this is what we call factorizable Harer-Zagier transform, because you see it's a product of just factorized monomials of this form. And this is not only true for the trefoil, but in fact for the whole family of torus knots, another example I show here. And basically, the generalized version of the factorizable Harer-Zagier is written in this way, where basically the variable m is a lower bound for the breadth index of the knot. And now, whenever it can be written in this compact way, everything that HOMFLY polynomial knew about is encoded in these exponents alpha I and beta I, corresponding to the numerator and denominator. And we have been able to find also an exhaustive list with up to 13 crossings of hyperbolic knots that have this property. So here is our list. So it's quite few among the thousands of 13 crossings knots. But in fact, many of them belong to this pretzel family that I draw here. So, and we also found that there is some twisted torus knots that satisfy this property. And what do I mean by that? So here I drew a braid, which basically up to this point, it corresponds to the torus knot T45. But these extra integers tell us to take the last 3 strands, for example, and introduce K full twist. And here I just draw one, so that the closure of this braid would be the twisted torus knot. And similarly, there is a notion of Harer-Zagier factorisability for links. But now the difference is that there is one factor that comes with a plus rather than minus sign in the numerator. And this is true for 2-stranded torus links, such as the Hopf link, but is no longer true for 3 or higher strands. And we also have a list of hyperbolic cases, but now the relative orientation of the 2 components becomes important. And this is what this bracket notation denotes. For example, we label this choice of orientation by 0, then reversing one of them would correspond to the notation 1. And we also have some twisted torus links, and you see here, basically, they are defined as before, but we have, one component closes back to itself when we take a closure, so it becomes a link. And what is interesting about these knots and links is that they can be related to one another by 2 operations. And this we call the full twist and the Jucys-Murphy twist. And here I show you an example with 3 strands. This is what this sublabel denotes, but can be applied to any number of strands. So full twist is basically taking a 3-strand braid and fully twisting it once, while Jucys-Murphy is just taking 1 strand and bringing it around and taking it back to where it started. And for example, if I start with a braid representative of the knot 5-2 and attach a full twist to it, like this, then it will result into the knot 1,039. While if I would attach a Jucys-Murphy twist to it, then I would get the knot 1,061, which both are also factorizable. And in turn, I could just start from this 3-stranded version of the trefoil knot and attach a full twist to get 5-2 itself, or alternatively, I could obtain it by some 3-stranded version of a knot with the Jucys-Murphy twist. And what I just described is nicely summarized in this factorisability map. So you see, for example, if I start with this three-stranded trefoil and do one full twist, which corresponds to the diagonal direction, I get 5-2. Another full twist takes me to 1039. While if I start from this one and I do a Jucys-Murphy, I get 5-2. And another Jucys-Murphy takes me to 1061. And basically all of the list up to 13 crosses is included in this nice map. And this is for three-strand braids, but for four-strand we have another map. And similarly for links, we can do the same, starting from like some three-stranded version of torus links with two strands. Then we do Jucys-Murphy and full twist to get all the other ones. And furthermore, we can actually apply the full twist an infinite amount of time or an arbitrary amount of times that we call k, and the factorisability property is still preserved. As you can see in this example, so this was 5-2, and I put k full twist, and basically the effect on the Harer-Zagier is additive on the exponents, depending on the number of full twists I include. And similarly, I can do this with the Jucys-Murphy twist. So starting from this configuration, attaching k full Jucys-Murphy, I again get an expression that depends on the number of times I include those. So to understand why this works, it's helpful to consider the so-called character expansion for the HOMFLY polynomial that was proposed by the same group of theoretical physicists. So this is basically taking an m-strand representative of a knot, so belonging to the braid group with m strands, which basically contains words of this form, with sigma I being the generators. Then we can write the HOMFLY polynomial of that knot as a sum over Young tableau, which are partitions of M. And basically here, W is just the right of the diagram. And yeah, we are summing over Schur functions, which are given by this expression here in terms of the hook length formula for the Young tableau. And they come with some coefficients that we call the Raka coefficients, and they're basically obtained by the trace of the braid work with the braid generators replaced by these R matrices. So we'll see how this works in the case of two strands. So let us consider this a normalized version of the Schur functions, which just cancel some of the factors. And then for two strands, we have the B2 group generated by just one element. So the braids will be of this form, sigma 1 to some power, which will be equal to the right. So then we have two possible Young tableau, and these are the corresponding Schur functions. And then the R matrix will just be equal to Q. It's not a matrix, it's one by one in this case. And then we have the coefficients for this Young tableau being Q to the right, while for this one, which is the mirror image of that one, we get Q replaced by minus Q inverse. And then in our favorite example of the trefoil, we have, which is has this braid representative. We can write this down. So we have a to the cube, and then q to the cube times this Schur function minus the other one. And then we get the familiar answer that we found before. And on three strands, similarly, like now we have two braid generators. So the braid words will be of this form. And we have three Schur functions now. The coefficients for the for these two are the same, but for the hook Young diagram, it will now become trace of product of some of these R matrices that are given here. So R1 is just diagonal Q and minus Q inverse, while R2 is some rotated version of that. And then we can apply the, we can look at the example of the trefoil, but now since torus knots are symmetric in M and N, we have a three-stranded version of it with this braid word, which now has right 4, but then the result is still the same as we expect. And this is useful because all the A dependence is contained in these Schur functions, or we introduce this hat to also include the overall factor A to the right. And then we can basically write down the Harer-Zagier as a sum over Harer-Zagier of the sure functions. So in the 3 strands example, we can just write down compact closed formulas for the Harer-Zagier of the sure functions, which are fixed, and then the coefficients will be the ones determining the Harer-Zagier for a particular knot. So we can write down this formula for the Harer-Zagier of any 3-strand knot, which only depends on this coefficient. So from this, we can see that factorisability will occur whenever this coefficient can be written as a symmetric polynomial with some highest power that is an even integer, and it's of this form, so that when multiplied by this thing, it will cancel. Many of these terms will cancel, and it will just give us a nice factorized expression. And the reason that full twist and Jucys-Murphy twist preserve factorisability is because their effect on the coefficient is to leave it invariant in this case. Well, in this case, it maps it to something else, but still of this form. So then no matter how many times we apply full twist or Jucys-Murphy, if we start from something that has Harer-Zagier factorisability, it will end up on something that again has that property. And what is really interesting also about this property in the Harer-Zagier factorisability is that according to our conjecture, it implies some relation between the SUN and SON plus 1 invariants. So this comes as a relation between the HOMFLY and the Kaufman polynomial, or rather this hat version of it, which basically involves taking the even part and then subtracting the odd part times this factor, which makes sure that also becomes even. And then there is a great simplification that occurs so that it can then become equal to the HOMFLY polynomial. And we are finding that this occurs exactly whenever we have Harer-Zagier factorisability in all cases that we consider so far. And in fact, this relationship was proven long ago to be true for just torus knots. But these people suggested there should be more families that satisfy it. And indeed, we were able to show that several of our infinite families, such as the ones I list here, also satisfy this property. And finally, let me also mention that given this nice factorizable formula for the Harer-Zagier, we can always invert it to write down a closed formula for the HOMFLY polynomial of these families, which will basically depend on the alphas and the betas. And this can be specialized further to the Jones polynomial, which is the special case at A equal Q squared, which can then be written in this very nice compact form where all the exponents of the numerator come with a minus sign and the exponents of the denominator come with a plus sign. And this can be nicely observed in the Kovanov homology of the knots. So you see here, basically the Jones polynomial is written as a sum over Q to the J, which J are the values here, and the coefficient is the Euler characteristic. So indeed, we see that 9 that corresponds to the numerator has Euler characteristic -1, while the denominator exponents, which are listed here, have Euler characteristic +1. And it's also interesting to note that for homologically thin knots, which means that their Kovanov homology table is restricted in these two main diagonals, then we have that Harer-Zagier plus signature of the knot is fully equivalent to Kovanov homology. So with this, let me conclude that Harer-Zagier is a very interesting tool as it encodes the information of the HOMFLY polynomial in a very economical way in just some sets of integers. And it also illuminates some relationship between the SUN and SON invariant, and also some connection to Kovanov homology, but also with AD singularity theory that I not have time to mention, but you can find more details in this preprint. And now we're currently working on finding a character expansion for the Kaufman polynomial, which might illuminate how to prove our conjecture. And with that, I would like to thank you for your attention.